Now the second of our, well, let me say something, go back, say something about number one. Remember, there's two topics they were hitting on before we get to thin film interference proper. The first one had to do with phase shifts, how I took that red wave and I shifted it a half a wavelength. And when I did that, the two waves went from constructive interference to destructive interference when I shifted it by a half a wavelength. Would have been the same effect if I'd have shifted it by 3 halves or 5 halves of a wavelength. Okay, as long as it was an integer number of half wavelengths, or an odd number, I should say an odd number of half wavelengths, that's the way to say it, an odd number of half wavelengths, that phase shift, then we go from constructive to destructive. And had we started out with destructive interference, and I had shifted my pink wave a half a wavelength, or 3 halves a wavelength, we would have gone from destructive to constructive interference. So a relative shift of half a wavelength between two waves takes you from constructive to destructive, or from destructive to constructive. But what I didn't say is that if I had shifted the pink wave a full wavelength, then we would have gone from constructive interference back to constructive. If we had started with destructive interference and I'd shifted the pink wave or either one of the waves by a full wavelength, we would have gone from destructive to destructive. So a full number of wavelengths, 1 wavelength, 2 wavelength, 3 wavelength shifts, take us back to where we started, whether we started at constructive or destructive. An odd number of half wavelengths, lambda over 2, 3 lambda over 2, 5 lambda over 2, takes us from constructive to destructive or from destructive to constructive. It takes us from one to the other. So an integer number of wavelength shift, relative shift, takes us back to where we started. An odd number of half wavelengths takes us to the other, whether we're going from constructive to destructive or from destructive to constructive. All right. So that was our first topic. We're leading up to thin film interference. The second one is one that we've talked about before. It's not too tricky, but I want to make sure that you remember it because it's going to come up. Okay, these two topics are going to come up, and I'll mention them when they do. Suppose we have a situation like this. Suppose we have a piece of glass. Okay, this is a side view of the glass. Let's say that n equals 1 point. What do I have here? 3. That's actually really low for glass. It should be 1.5. Let's say it's water. Let's stay with glass, doesn't matter. Let's just say it's really low density glass. Okay. If we take, let's see, what color do I have here? A nice green laser. Okay, the green here is rather disappointing. But if we take a nice green laser and shine it through the glass, okay, lambda is about 520 nanometers for this wavelength for green. Okay, the green laser that we played with in class that day, it's about 520, maybe a little bit less, but something like that. Okay, when it enters a new medium, the wavelength changes. Okay, it gets less. The wavelength in the medium is equal to the original wavelength divided by the index of refraction of the medium. The wavelength gets less. So in this case, we'll just call it lambda sub m. Lambda inside the medium is 520 divided by 1.33 nanometers, which is actually, let's see, I did the math here, 391. So inside the glass, the wavelength of that green laser is not 520, it's been reduced by a factor of n, and so we are, rather of 1 over n, and so we now have 391 nanometers. So out here, the wavelength is relatively long. Inside, it gets shorter. And then when the light re-escapes out into the air again, okay, so air, and air, the wavelength returns to its original value. Okay? But inside of a medium, whether it's glass, whether it's air, whether it's water, whether it's soap, whether it's oil, doesn't make any difference, whether it's plastic, diamond, the wavelength gets reduced. Now the color is the same, the frequency stays the same. Okay? Frequency remains the same. So the color doesn't change. The color doesn't change, but the wavelength changes. Okay? That's the second thing. We've already covered this. We talked about the change in speed, change in direction, talked about refraction. We did cover this before, but it's going to be really important as we talk about thin film interference. Now the next video up we're going to look at is a video from YouTube, and it simply demonstrates for you thin film interference. You see it when you do soap bubbles in the sunlight, nice swirly greens and blues and so forth. That's where you probably are most familiar with it. Oil and water is another good example of it. I think in the video that's going to show you a soap film that has been stretched over a ring and show it to you over a few minutes and how the colors and so forth change. That's thin film interference, and this business here about the change of wavelength is one of two ideas we need to have as we prepare for this. So next thing I want you to do is watch the video on YouTube, the demonstration video with a soap film. And then after that, we'll come back and we'll do a careful discussion about what's going on there. All right, and it's going to use both of these ideas we've covered already. All right, so I'll see you then.